Hi, good morning, everybody. My name is Chenguang Zhu. Today I'm going to talk about reducing inefficiencies in taxi systems. This is joint work with Professor Balaji Prabhakar from Stanford University. Taxis are vital to modern urban transportation systems. The flexibility and 24/7 availability make taxis a perfect complement to public transportation. In recent years, the rapid increase in demand for mobility has prompted the booming of taxi industry in terms of both fleet size and scale of taxi trips. However, accompanying with the booming of taxi industry is various problems. For example, an excess of taxis will not only lead to a waste of resources, but also hurt the profitability of taxi industry. What's more important, an empty fleet of taxis are a significant cause of congestion themselves. To cure these problems, governments have enacted entry regulations for both drivers and taxi vehicles. However, one needs an accurate estimate of an appropriate size of taxi fleet to satisfy the need for mobility of urban dwellers. Actually, if we take a step back and look at the taxi systems, it is in essence a demand and supply system in which passengers become the demand side and the vehicles and drivers become the supply side. And the two sides interplay with each other. In a typical taxi system, there are thousands of taxi vehicles and hundreds of thousands of passengers. In such a complex system, it can easily occur that we have a lot of inefficiencies. Let me illustrate this with this animation. So here I'm showing 4 taxi trips. For each taxi trip, I indicate the start location with the ring and the end location of that trip with a solid circle. And the same color indicates one trip. Now let's see how several taxis can finish these 4 trips. The first taxi takes this blue trip, then it goes on to the start location of the purple trip. Here we use the dashed green line to indicate the idle time or idle distance. Then it takes this purple trip. The second taxi finished the red trip, while the third taxi did the green trip. So in total, we have used 3 taxis to finish these 4 trips. And here is the incurred idle distance and idle time. However, by rearranging the taxis in a smarter way, we can actually do better. So here, say the first taxi finishes the blue trip, then the red one, and the green one, while the second taxi did the purple one. So in total, we only need 2 taxis to finish these 4 trips, and the incurred idle distance, idle time is shorter. With this comes our goal. Assuming that the start and end locations and time of each trip are fixed, we want to reassign all trips to possibly fewer taxis. And at the same time, we want to reduce the idle time, as it is directly correlated with the inefficiencies. Before I introduce my model, let's look at a model from previous literature, as it is closely related. In that paper, the model was called path cover model. And the problem was formulated as a graph in which every trip is modeled as a node Pi. And we connect an edge from Pi to Pj if and only if it is feasible to finish trip Pj after Pi. So in the end, we end up with a directed acyclic graph, or DAG. The reason is that temporally, we must finish a trip first before the other one. Now, the trip sequence of each taxi forms a directed path, like this red one. It follows that a valid path cover of this graph corresponds to a valid assignment of trips to all taxis. Therefore, in order to minimize the number of taxis used to finish all these trips, we only need to find the minimum path cover in the stack. And fortunately, we have a maximum matching algorithm to solve this efficiently. The good thing is that this model can provide the optimal solution, and it can give a detailed assignment plan. However, the biggest con is scalability. In this graph, the number of nodes is equal to the number of trips, and the number of edges is approximately the square of the number of nodes. However, in a typical city, we have a lot of taxi trips, For example, in New York City, on a normal day, we have more than 400K taxi trips. This translates to 160 billion edges. And if you add in the complexity for the maximum matching, it is not doable. So to work around this problem, the previous model just considered each short time interval of 10 minutes and assign the taxi trips in each short time interval. However, this significantly reduces the importance of this work, since the assignment in the previous time interval cannot be merged with the next time interval, as the taxis assigned are still working. It follows that this model cannot even obtain an assignment over the whole day. So to cure this problem, we use a different approach, which can give a detailed trip assignment. And at the same time, we give various insights into directions of improvement to the current taxi system. Our model is network flow based in a spatial temporal network in which vehicles are represented by flow and trips are represented by edges with capacity limit. Okay. The first step in our model is discretization. For time, we partition the time axis into bins of 1 minute and put the start and end time of each trip into the bins. For location, we partition the city into regions. In the experiment, we took data from taxis in New York City. So we partitioned the New York City into 36 regions based on district boundary and main roads. Now, using this discretized time and location, we can construct a graph in which every node PTL represents the fact that a taxi is in region L at time t. So we have this matrix network. For example, this node represents that a taxi is in region A at 3 p.m. Now, with this network, we can depict the actions of taxis using edges. Firstly, an idle taxi can stay in the same region for the next minute. This can be captured by these horizontal edges. Secondly, an idle taxi can move from its current region L to the next region L prime. This can be captured by these parallel edges. And the time to traverse from one region to another can be obtained from the data. The third type of edge is the most important one, the trip edge. Suppose a trip starts in region L at time t and ends in region L prime at t prime. We construct an edge from the PTL to PT prime L prime, which is this red edge. Now, if we consider each taxi as a flowing particle, then every edge should have a capacity limit, both an upper limit and a lower limit, which dictates how many particles can flow through that edge. And for idle edges, it trivially has a lower limit of 0 and an upper limit of infinity, which are these blue edges. However, since each trip has to be assigned to one and only one taxi, so the edge must have both its upper limit and lower limit the same as the number of associated trips. For instance, if there are two trips starting in region A at 3 p.m. and ending in region B at 3:03 p.m., both the upper limit and lower limit of that edge should be 2. Okay. Now to finish the construction, we add a source node S and sink node T. Then we connect S to trip starting nodes and from trip ending nodes to T. Now, with this construction, each taxi hypothetically starts from node S and ends at node T. In other words, we can depict a taxi's day of work using a particle flow. It always starts from S, goes through this alternating work and idleness cycle, and then ends at T. For instance, this node, this taxi, starts to work at 3 p.m. in region A and takes one trip, ends in region B at 3:03 p.m., and then finishes his day of work at D. So far, we have talked about the graph, but how does it connect to network flow? We have illustrated that one working taxi corresponds to a 1 unit flow from S to T and vice versa. It follows that a feasible flow in this graph network corresponds to a valid assignment in which all trip requests are satisfied. Then, minimizing the number of required taxis is equivalent to minimizing the feasible flow. Fortunately, we have off-the-shelf algorithm to efficiently solve this problem. Remember, we also want to reduce the idle time. But this turns out to be easy. For all idle edges, we can associate the length of idle time as cost. For example, it takes 1 minute of idle time to stay in region A from 3 p.m. to 3:01 p.m., so the cost of that edge is set to 1. And all the other edges should have costs of 0. Now, with this cost, we need to compute the minimum cost and minimum feasible flow, which again has a good algorithm to solve. But we are not done yet. Now we only have a bunch of flow values. What we want is a valid assignment, but it's very simple. After we get all the flow values, we can employ breadth first search, or BFS, on edges with a positive flow from S to T. And then each path determines the actions of a taxi, which is that alternating work and idleness cycle. This model is much more scalable than the previous one, since the number of nodes in this network is a constant, because we have discretized both the time and location. And the number of edges is bounded by the square of number of nodes. Now let's look at the evaluations. For dataset, we took all the trips made by yellow taxis in New York City, which was from a public dataset released by New York City and Taxi and Limousine Commission. We took a 12-hour shift data from 4 a.m. to 4 p.m. on May 15th, 2013, which was a normal Wednesday. In this time interval, there were over 214,000 trips made by 12,000 taxis. We implemented the flow network, and this is the number of nodes and edges in the network. This is a configuration of the machine on which the experiments were run. For the minimum feasible flow algorithm, which we denote by FF, it ran for less than half a minute. And for the minimum cost and minimum feasible flow algorithm, MCFF, it ran for a little bit more than 4 minutes. Now let's look at the results. So in the real data, more than 12,000 taxis were used to finish those 214,000 trips. However, under the network flow models, we only need to use 8,800 taxis, which is a 28% reduction. And MCFF likewise has 8,900 taxis. Naturally, each taxi takes more trips. However, the idle time per taxi drops from 4.1 hours per taxi in real data to 3.5 hours in FF, and further down to 2.8 hours in MCFF. And of course, the earnings per taxi goes up by almost $100 per taxi. So in other words, in our models, taxis can be better utilized. This can be also seen from the utilization rate. Here, this metric is defined as a metric over time. So at time t, the utilization rate is defined to be the number of taxis taking trips at time t divided by the number of taxis working at time t. A taxi is defined to be working between the start time of its first trip and end time of its last trip. A higher utilization rate leads to a less waste of resources. So here, let's look at the utilization rate. The x-axis is the time of the day. The y-axis is the utilization rate in percentage. The blue curve is for the real data. So as you can see, in the morning peak hours from 7:30 to 9:30, the average utilization rate in real world is about 82%. However, in the network flow models, FF, it increased to 87% and further up to 92% in MCFF. So the utilization rate increased a lot. Up to now, we have observed the performance of taxis in general. But now let's look at some examples of particular taxis. So here we take 30 randomly sampled taxis in real data. X-axis is the time of the day, y-axis the vehicles. Every row indicates one particular taxi, and every segment indicates a trip. So we see a lot of gaps here. These gaps actually mean the idle time. there are a lot of long gaps here, which is related to inefficiencies. We also randomly sample 30 taxis in FF. As you can see, each taxi makes more trip, and the gaps are much shorter. And likewise for MCFF. So in other words, in the network flow models, taxis are wasting much less time. We also implemented the path cover model we mentioned beforehand. As I have said, in that model, if we construct the whole graph, there are too many edges. So here, we only consider trip pairs ij if they are not more than 5 minutes apart. But even with that, we end up with 135 million edges, which is about the limit of that machine. With this constraint, actually, our model still does better. So the path cover model has over 10,000 vehicles, and is run more than 10 times slower. Last, I'm going to talk about what we can learn from the models. So we want to explore patterns of assignment given by the models. This is important for both the taxi operators who can spot inefficiencies in the current taxi system, and also individual drivers who can assign trips in a smarter way. Let's see how to find the next trip. Here we define a taxi crosses region to take its next trip if the end location of the previous trip and the start location of the next trip are in different regions. The region is defined by that location discretization. More region crossings indicate that the driver searches farther for their next trip. In this plot, I'm showing the number of region crossings for real data and the two network flow models. The x-axis is the time of the day, the y-axis is the number of region crossings. The blue bars are for the real data. As you can see, in the network flow models, the number of region crossings dropped by 30% to 40%. So this indicates that for a better assignment, drivers need to search closer for their next trip. Airport trips. As we know, airports are usually far from residential and business district. For example, JFK Airport is about 18 miles from Manhattan. On the other hand, airport trips are really popular. 2.2% of all observed trips start from or end at JFK. So now, drivers face a choice after they drop off a passenger at JFK. Should they wait at the airport for their next passenger or leave the airport without any passengers? This choice makes a difference. In the real data, we found that fewer than half of the taxis sending passengers to JFK come back with new passengers from the airport. However, this ratio increases dramatically in our network flow models to 67% for FF and 64% for MCFF. The takeaway message is, drivers, you should wait for your next passenger more often at JFK. This conclusion is very interesting because we never told the models to let the drivers wait at the airport. By increasing the utilization and making the assignment more efficient, we automatically reach this assignment and this property. To summarize, in this talk, I introduced a new method to reduce inefficiencies in taxi systems. And I introduced two network flow models, which are much more space and time efficient than previous ones. And I also talk about how to learn from the assignments given by the models to increase the efficiencies. Thank you very much. Any questions?